Hello students, my name is Mr. Moncada. I'm going to be your Physics 3 teacher for Proyecto Science this summer. In Physics 3, we're going to be looking at topics such as sound waves, simple harmonic motion, and sound. But before we do that, I think it'd be a good review to go over what you may have done in Physics 2. So to start off, one of the first topics you may have seen in Physics 2 is momentum. Now, what momentum is this equation right here. P is equal to mv, where P is our momentum, m is the mass of our object, and v is the velocity of our object. So what momentum shows us is basically how fast is an object that has mass is going. So you can think in terms of like a car, a car has a certain mass, and depending on how fast it's going, it's going to have a certain type of momentum. So obviously, if it's going slow, it's going to have lower momentum than if it's going fast. Now, an important concept when dealing with momentum is something we call the conservation of momentum. So, conservation of momentum. So what this basically means is that your momentum initial should equal your momentum at the end. Now, you can think of this, an example would be, let's say you have a wall, right? And then here you are, and let's say you're playing soccer, right? If you have a ball and you kick it towards the wall, and you kick it so that it has a momentum initial, right? When this ball hits the wall over here and it bounces back, we should expect it to come back. We should expect the ball to come back with the same momentum. So this would be, showing us that the initial momentum is equal to the final momentum. An example would be, if you've ever seen those videos of people that grab those gym balls and they run into each other and then they like bounce apart. That's basically what's going on. So moving on with momentum, we showed that our momentum initial should equal our momentum final. Now there is an exception to this, and that is when we introduce the concept of impulse. Now, what impulse is basically a change in momentum that happens, right? So, let's say, for example, if I kick my ball, right? Let's stick with the same example from here. If I kick my ball, but then it doesn't bounce back and it stays at the wall and it sticks there, right? It is not moving anymore. Its velocity is now 0. So that means its momentum is 0. Its momentum at the end is 0. Now, this breaks our idea of conservation of momentum because, well, when we first kicked the ball, right here, it had a velocity that we applied when we kicked it. But then, now that the ball is stuck to the wall, it's not moving. So what happened to the momentum? And that is what we call impulse. There was a change to the system that caused our momentum to not be conserved. And we call that J for impulse. Okay? Now, these are important things that you guys should understand. I'll be giving you guys some problems that we can go over after. That way, you reinforce the learning that you've already done. Now moving on, we're gonna just do a light overview over rotational kinematics. So, rotational kinematics. Now, I'm sure you remember kinematics from when you took Physics 1. Now, normally we have our velocity, our acceleration A, our displacement D or X, displacement. But these values right here deal with linear kinematics. For rotational kinematics, we have omega for angular velocity. We have alpha for angular acceleration. And theta for angular displacement. Now, an example for this would be, here, just label this is rotational kinematics. Now, you may remember how in linear kinematics you have some of your basic equations that you use to solve your problems. So, for example, you had your v final is equal to your v initial plus your acceleration times time, right? In rotational kinematics, you have similar equations, except we're not going to use the linear values for them. Instead, we're going to use the angular values for them, the rotational values for them. So, for example, instead of using v, we're going to use omega. Instead of using a, we're going to use alpha. So this first equation would become omega final is equal to omega initial plus alpha t. Now, this equation over here gives us the velocity if we were dealing with a linear problem. This would give us the angular velocity if we were dealing with a rotational problem. And there's many different similarities between rotational and linear kinematics, which you'll encounter as we progress through the course. But for now, this will do in terms of just a brief overview. Next, I'm going to mention centripetal forces. So a centripetal force is, let's say you have a yo-yo, right? It's attached to a string and it's spinning around in a circle like this. Whenever you have a system such as the one I just illustrated, you have something that we call a centripetal force that's present. So what this basically means is because there's this string right here that's pulling this yo-yo, basically that's preventing the yo-yo from going out flying and it's keeping it in the circular motion, we have this centripetal force, which is basically a force that just keeps pointing towards the center. Now when we have this type of force, we'll call it force centripetal. Normally from Newton's second law, we were used to seeing this equation right here. We would see F is equal to ma. However, because we have a centripetal force here, our acceleration is not linear. It's gonna keep changing as it progresses, right? If it was a linear acceleration, the yo-yo would just keep going like this, or it would keep going straight. it wouldn't rotate in a circle. So we draw the similarity where we have acceleration is equal to v squared over r. And this is the case for centripetal force problems. So then our F is equal to ma equation is going to become F is equal to mv squared over r. And this is the equation for centripetal force. Now there is one last topic that we need to go over from physics 2, and that is torque. So what torque is, it is the angular equivalent or the rotational equivalent of force. So I showed you already that velocity has omega for angular velocity as its equivalent. The a in acceleration has alpha for angular acceleration, and the x or the d for displacement has the theta for angular displacement as similars. There's a few more that I'm going to write down. So for linear, I'll write linear over here. We had force, which stands for force. We also had mass. But for angular problems, we're going to have torque. And torque is denoted by the Greek letter tau. It's like a small t with like a few squiggles. So this is torque. And lastly, instead of mass, we're going to have I, where I is the center of mass. And don't worry if you feel like this is a lot. Again, this is just a brief overview, and of course, any questions that you may have, you can ask them after the pre-recorded video is through. Going forward, this is how the class, you should expect the class to be run. It's going to start off with a pre-recorded video where I go over what our goals to learn for the class are. And then after, we'll have like 30 to 40 minutes of discussion where you can ask any questions. You can be like, oh, Mr. Mokata, can you explain this part from the video? I didn't really get it, and I'll gladly help you out. That's what I'm here for. So yeah, just to finish off with torque, like I wrote before we had F is equal to ma for linear. For angular, if instead of using these linear values, we use the angular values, we see that F is equivalent to torque. So instead of writing F, let's write the tau for torque. Okay? We see that M has the equivalent of center of mass. So instead of writing M, let's write I. And lastly, instead of A, we're going to write alpha for angular acceleration. And this right here is the equation for torque. Now, I hope you're taking notes on this. This is just a brief overview of everything that you may have covered in physics 2. There may be some things that I skipped out on, but I feel like this is what you're going to need going forward into what we're going to be doing in physics 3. And any questions, you can bring them up now. And yeah, I'm very excited to work with you guys this summer. I hope to teach you, interesting stuff, and I motivate you to pursue physics a bit further. Thanks, guys.